What's going on with the tail? Is this now just a normal comet off-gassing, or, as at least one of your colleagues has suggested, is this thrust from some sort of alien tech that's like maybe stepping on the brakes a little bit?
When the James Webb Space Telescope turned its infrared eye toward 3I/ATLAS, the international astronomy community expected a useful piece of data, another interstellar visitor to catalog and compare with the few that had come before. What Webb returned was not a routine readout. It was a set of images and spectra that forced people to stop and rethink everything they thought they knew about comets, about interstellar objects, and about how lifeless lumps of rock and ice behave when a star wakes them from their long sleep. The first, most obvious surprise was the light itself, a deep, steady crimson glow filling the object's coma. It was not the pale scatterlight halo of a water-rich comet. It was not a thin fan of dust. It was a broad, symmetrical red envelope that spread like a calm storm around the nucleus, and it did not flicker. It held color and form with an unnerving, machine-like steadiness. At first, observers tried to make the simple explanations fit. Maybe the red came from dust grains that just happened to be the right size to redden the infrared. Maybe the image processing had introduced a color bias. Maybe the comet's orientation and motion had created an optical effect, but Webb's spectrum would not allow those tidy fixes. The signatures in the near-infrared pointed to carbon dioxide, CO2, as the driver. The lines that mark CO2 lit up strongly, while the familiar water vapor features barely registered. In short, the coma was dominated by carbon dioxide emissions and not by water. For a body at that distance from the sun, that was unexpected. Water is normally the first volatile to wake and produce the bright, frothing comae and tails that make comets spectacular. 3 Atlas behaved like it had a different internal rulebook. The more teams looked, the stranger the object became. Early size estimates, calculated from simple brightness to radius assumptions, did not add up. Hubble images suggested a small nucleus, a compact solid perhaps a few hundred meters across, a size that would classify the object as unremarkable. Later scans with Webb and other infrared-sensitive instruments painted a different picture entirely. The reflected and emitted light intensity at certain wavelengths hinted at a much larger reflecting surface than those small sizes could explain. Some models that tried to reconcile the data suggested a nucleus tens of kilometers across, far larger than expected. How could something that large have slipped by sky surveys and ancient catalogs for as long as it apparently had? That was the first major riddle. The object's apparent scale did not match the obvious classical indicators. A second riddle concerned the way the light was being reflected. When starlight bounces off a natural surface, it scatters in ways that leave a fingerprint, a pattern of randomness, roughness, and irregularity. What Webb and follow-up teams reported instead was smoothness. The light curve was unnaturally regular, the reflectivity curve too consistent across angles to be comfortably placed in the box of natural, unprocessed rock and dust. Some scientists described it as too polished for a typical comet, a surface that acted more like a gently textured mirror than like a battered, pitted chunk of primordial ice. When researchers tried to model particulate scattering to explain the effect, the models required grain properties and spatial arrangements that did not look natural unless some external process had forced them into shape. That is where concerns moved from curiosity to unease. If the coma's color and composition were odd, and if the reflective behavior suggested an unusual surface arrangement, then the question shifted to why. One idea was geological. Perhaps 3 Atlas had formed in a region very different from the zone where our solar system's comets were born. If its native disk was colder or chemically distinct, CO2 could have frozen in greater abundance, producing a body whose chemistry is dominated by carbon dioxide rather than water. Another idea was evolutionary. Over millions of years traveling between stars, cosmic rays, and interstellar particle bombardment can alter surface chemistry, driving off more volatile water and leaving behind CO2-rich layers. Those are plausible, scientifically grounded possibilities. They are not comforting if the object behaved in other ways that suggested active regulation rather than passive alteration. The motions of 3 Atlas raised more alarms. Trajectory analyses indicated a path through the solar system that was not merely hyperbolic, not just a one-time free flyer passing through with an unpredictable path, but oddly precise. When teams reconstructed the object's course backwards and forwards, they found subtle, repeated micro-adjustments. These were tiny shifts in angle, barely measurable, but consistent over time and at levels that natural torques should not easily produce. Natural forces like outgassing jets can produce small course changes, and comets do correct their paths under those forces. Yet the pattern here appeared deliberately small, like tiny nudges rather than chaotic drifts. When astronomers cross-checked against the timing of perihelion passes or planetary approaches, they found that 3 Atlas seemed to brush past certain regions of the inner system with a regularity that, at best, suggested some kind of navigation, and at worst implied a directed trajectory. Those who prefer natural explanations invented ever more complicated scenarios, shadowed pockets of volatile release timed by internal insulation, rotating jets that produced regular torque, or interaction with a thin stream of interstellar medium that functioned like a groove in space. Yet each such answer introduced its own problems. No natural mechanism readily explained both the very symmetric red coma and the precise repeated course corrections. And that dissonance widened the space where more speculative and more uncomfortable hypotheses could live. Among researchers, whispers circulated not as facts, but as questions. What if the object were not merely passive? What if it was controlled or structured or even carrying systems designed to behave in particular ways when heated? Then came the spectral oddities that troubled the biologists and chemists who peer at molecular patterns. Webb, Hubble, and ground-based telescopes reported an arrangement of organic molecules that did not read like a random stew. The visitor expelled methanol, carbon monoxide, formaldehyde, and cyanide, all compounds known to cometary chemists. But the ratios and layering of those molecules appeared organized rather than scattered. The distribution of organics, when mapped with enough spatial resolution, showed stratified shells and repeating patterns. That layered, patterned chemistry raised a provocative question. Were these distributions the result of natural layered formation in a particular protoplanetary disk, or did they show a higher-order structure that hinted at purposeful assembly? The latter suggestion pushed debate into territory where scientists must speak carefully. Science requires testable claims, and design-like signatures rarely survive careful falsification. Still, the data were unusual enough that teams specializing in prebiotic chemistry and molecular patterning flagged the results for deeper scrutiny. Parallel to the chemistry puzzle was an electromagnetic event that pushed feelings into raw fear. On a quiet morning, radio arrays picked up a narrow band pulsed signal that seemed to move with the object. It was brief and repeated, with a tone that some engineers described as mechanical, a pulsed synthetic note with a harmonic structure suggestive of deliberate emission. SETI teams and radio observatories rushed to check for terrestrial interference, satellites, and instrumental artifacts. Many false alarms get ruled out that way, but multiple independent receivers confirmed the waveform, and its apparent source tracked with 3 Atlas. The tone lasted for only minutes before fading. When SETI teams tried to triangulate and study the source further, system logs showed strange anomalies, data corruption, temporary loss of antenna pointing, and in a few cases, the bizarre wiping of local backups. Engineers who had been involved in those observations later described prolonged technical problems on their equipment that matched no standard failure mode. Those malfunctions were quietly handled, with NDAS and internal reports. Officially, agencies cited weather and software glitches. In private, several people involved said they experienced the event as a breach of the normal order of monitoring. Something in the environment had responded actively to observation. The more technical analyses dug, the more unreal some facts seemed. When Webb's instruments peered deeply at the object's core with high-sensitivity infrared measurements, the expected faint thermal glow of a cold nucleus was absent. Instead of a low, wavering black body curve, instruments reported an almost perfect zero signal in some bands where emission should have been measurable. In other words, the core seemed to radiate nothing detectable at those wavelengths. That is impossible for any known material at any temperature above absolute zero. Everything radiates. If an object shows no thermal emission in bands where temperature readings are standard, then it either possesses exotic radiative properties, or the measurement is missing some critical aspect of the object's interaction with space. Some teams suggested that an absorbing coating, ultra-thin and perfectly tuned, could be masking the core. Others proposed it might be a hollow region, a void. A frightening hypothesis from a few physicists posited that the object could be cloaked in some way that suppresses thermal emissions, effectively rendering its inner mass invisible to these particular probes. As the data were filtered through different teams, analysts found another startling feature in the coma itself. The gas cloud, measured at many positions and times, repeatedly displayed fractal-like geometric patterns. Rather than a smooth, dissipating halo, the gas showed nested geometric forms, spirals and repeating polygons that recurred across frames and at multiple scales. Fractals can emerge in natural systems under the right conditions, but these patterns were unusually regular and persistent. Scientists tried Fourier transforms and other pattern recognition tools and found that the distribution of points and intensities correlated with mathematical sequences like the golden ratio and Fibonacci series. For most observers, the natural world's relationship to these sequences is abundant, but not usually so clean, repeating and space-filling in a slow-moving gas cloud. That raised another kind of question. Were these geometric patterns a byproduct of internal processes that produced periodic jets, or were they a kind of encoded structure? If encoding was a possibility, then encoding towards what purpose? That question brought in the most speculative and troubling insinuations. Bioinformatics teams, asked by observatories to fingerprint the organic molecules, found correlations between some molecular sequence distributions and patterns that resemble certain functional motifs found in terrestrial biology. The correlations were not a one-to-one match with DNA sequence, but some alignments with mitochondrial gene patterns and protein fold motifs were strong enough to warrant a second look. Skeptical researchers pointed out very reasonably that convergent chemistry can produce similar-looking motifs without implying shared ancestry. Organic molecules follow the rules of chemical bonding and energy minimization. Certain patterns will be common in many contexts, yet the overlap triggered uncomfortable scenarios in which the object might carry complex organic structures arranged in a way that could interact with planetary environments. Some fringe specialists floated the idea that this could be a vehicle for distributing chemical patterns that influence biology, not an infective agent, but a kind of biochemical nudge. This idea went from fringe to cautious discussion in some corners because of the way the molecules appeared layered and patterned, not random. Meanwhile, gravitational models added another eerie piece to the puzzle. Precision tracking showed minute perturbations in the predicted motion of nearby particles, and when researchers subtracted the visible mass from the models, a residual gravitational effect remained. That is, an invisible, mass-like influence trailed the object at a consistent distance. It behaved as if a second body of modest mass, perhaps comparable to a small asteroid, occupied the same general trajectory, but emitted no light, no radio, and showed no detectable thermal signature. Teams labeled it a gravitational ghost. Its presence changed the dynamics of dust streaming in the coma and affected how background starlight bent as the object passed. It is one thing to have an invisible mass due to unilluminated rock. It is another to have a mass that seems to respond at a distance while leaving no electromagnetic trace. That is the kind of finding that forces a long list of possible explanations. Hidden companion with a radically low albedo, an internal mass separated by a void, or something even less understood. The political and institutional reaction to the new data was another part of the story. A number of reports and internal logs, some later leaked or reported by journalists, suggested that international agencies were coordinating more closely than usual. There were encrypted bursts of activity across orbital sensor networks and, according to some sources, synchronized firmware pushes to a variety of observatory control systems. From the outside, these moves look like cautious housekeeping. From the inside, a rapid global software update implies that agencies were aligning tools, perhaps to standardize data formats or to push new analysis routines that could not be delayed. The speed and scale of these changes prompted conspiracy-minded narratives and also practical concerns. Why upgrade critical systems under a time crunch? Why limit public communication while internal activity accelerated? Officially, agencies cited the need to prevent misinterpretation and avoid public alarm. Unofficially, some people within the networks admitted to a growing discomfort. Data that had once been freely shared and casually discussed was being treated as sensitive. Other anomalies added an almost surreal layer to the unfolding picture. Timekeeping systems in several observatories and precision labs began to show small, transient desynchronizations correlated with the object's emissions. High-precision atomic clocks recorded tiny timing offsets during specific burst intervals. Satellite systems reported microsecond discrepancies in synchronization. Some otherwise stable arrays experienced brief phase shifts. The effect was faint, well within the noise for many systems, but consistent enough across multiple independent laboratories that researchers took notice. When a mathematical scaling of the emission intervals was applied, some analysts pointed out a match in a scaled way with Planck times, the fundamental quantum units of time. That numerical correlation is a red flag because Planck scale effects at astrophysical distances are entirely unexpected. Either one had stumbled onto an unprecedented physical interaction, or the correlation was a statistical fluke amplified by selection bias. Both options were unsettling. A separate set of observations seemed to suggest the object had an internal cold region held at temperatures close to absolute zero. Thermal maps indicated a sharply bounded spherical core at roughly 40 Kelvin, much colder than the surrounding coma and inconsistent with the active outgassing seen. A cold interior combined with active outflow produces a paradox. Boiling jets require heat, yet the supposed inner chamber radiated none of the warmth expected. Some speculated the object might harbor a cryogenic chamber, a preserved interior kept at low temperature to protect volatile materials or some other payload. That led to the provocative idea of a vessel-like structure, something designed to keep fragile contents frozen during long travel and then carefully release them when conditions are right. It is a theory weighted with dramatic connotations, and scientists engaged with it cautiously. Cryogenic preservation is a known engineering goal for certain missions. The idea that an interstellar object could carry such an engineered space was once relegated to science fiction. The new data nudged that boundary. Then, there were the so-called light echoes, faint, delayed reflections and shadows observed by high-speed imaging that lingered longer than expected after the object passed behind a star. Those echoes behaved oddly, persisting and shifting in ways not predicted by simple scattering and refraction. Some teams argued that gravitational lensing could explain a portion of the effect, but the echoes did not fade as a lensing event normally would. Instead, they seemed to leave behind faint imprints that moved with the Earth's motion and subtly changed with observation angle. A few theoretical physicists proposed a speculative possibility: temporal echoes, artifacts of a body that interacts with space-time in ways that create multiple apparent moments of itself. In simpler terms, the object might be present in slightly different temporal slices, and our instruments sometimes catch overlapping images. That claim is extraordinary and would require extraordinary evidence, so most scientists treated it as an intriguing but highly tentative idea. As the observational pileup grew, cultural and historical threads returned to public discussion. A small group of scholars, comparative mythologists and archaeoastronomers, began to point out descriptions in ancient myths that could be seen as describing a cyclical sky object: a red eye, a silent watcher, a return at regular generational intervals. Some of these associations were poetic and speculative, more about the power of metaphor than about direct evidence. Others involved specific, hard-to-explain alignments between dates and astronomical cycles in canonical texts. Scientists remained cautious. Pattern-seeking minds find meaning where none may exist. Still, the convergence of modern observational strangeness with age-old narratives stirred popular imagination and prompted serious historians to re-examine old records in a new light. Whether these correlations have any predictive or causal power remains an open question, but their reappearance in public conversation shows how an event in the sky can ripple across disciplines and cultures. Throughout all of this, the most responsible scientists held to a careful tone. They published data, shared calibrated spectra, and recommended simulations. They warned against jumping to sensational conclusions. Yet caution can feel like silence to an anxious public. For every carefully worded paper, a dozen speculative threads sprouted online. For every press release that asked for patience, social feeds filled with leaked images, decoded messages, and theories about deliberate visits. The truth, as so often is the case, lay somewhere in the middle, an observation that pushed the boundaries of current understanding and required months or years of careful cross-checking to fully unpack. What the James Webb data made clear, beyond the immediate oddities, is how little is known about the range of possibilities for objects that originate outside the solar system. Interstellar visitors are rare and, until recently, faint. They arrive without notice and leave quickly. When one does linger long enough for detailed observations, it can expose blind spots in our models. 3 Atlas is doing exactly that. Its crimson coma and CO2 dominance forced astronomers to revisit formation models, radiation processing, and the resilience of volatiles after long journeys. Its strange reflective properties forced teams to reassess how light scatters through dusty coma. Its micro-adjustments pushed orbital dynamicists to refine models that include non-gravitational effects. Its spectral oddities nudged chemists and biochemists to expand their catalogs of possible non-random distributions. Each anomaly was a thread, Pull enough threads, and the fabric of understanding unravels and must be rewoven. There are practical responses to such a broad challenge. Observatories coordinated more tightly, sharing calibrated archives with clear provenance and standardized metadata. Space agencies drafted contingency plans for more aggressive follow-up of future interstellar objects. Instruments were configured to prioritize near-infrared spectroscopy in the earliest observation windows so that crucial volatile signatures would not be missed. Modeling efforts multiplied, combining thermal conduction physics, cosmic ray chemistry, and fracture mechanics. And, perhaps most importantly, interdisciplinary teams forming around 3 Atlas began to include engineers, chemists, climatologists, biologists, and historians, people who rarely sit at the same table in day-to-day astrophysics work. That multidisciplinary posture recognized that an object like this is not just a problem of orbital mechanics. It touches practical engineering, planetary protection, cultural history, and the philosophy of how humans respond to the unknown. In private, many of the scientists who had spent late nights poring over spectra and light curves admitted to a mixture of excitement and unease. They relish puzzles because puzzles are what drive discovery. But a puzzle that resists repeated rounds of careful testing and that seems to show signs of design-like features changes the tone of that pleasure. The discipline must balance curiosity with caution, and the community must guard against errors born either from wishful thinking or from reflexive dismissal. In other words, the responsible posture is to test, to model, and to keep communication open, especially when public anxiety runs high. So far, nothing definitive indicates malicious intent or any threat directed at Earth. The object's perihelion and closest approach distances do not suggest an impact risk, and no deliberate act against the planet has been observed. Nevertheless, the very strangeness of the data argues for attention. If an object can possess internal organization, apparent cryogenic preservation, patterned organic layers, or invisible masses that distort gravitational fields, then our catalog of celestial phenomena must expand. Preparation is not panic. It is the mundane work of science, refining instruments, improving coverage, and developing models that can be tested with the next passing visitor. For now, the message from the James Webb data is this: 3 Atlas is an object full of puzzles. It is not merely another interstellar rock to be ticked off a list. It is a living laboratory for questions about formation, endurance, and the possible range of structures that can exist in interstellar space. Whether the object turns out to be an oddball natural formation, a highly processed relic of a distant disk, or something engineered and deliberate, the findings already have lasting effects. They change how observatories plan for rapid response. They change the questions theorists ask about disk chemistry and cosmic ray processing. They widen the aperture through which humanity searches for meaning in the night sky. People will keep watching, telescopes will keep measuring, data will keep arriving, and models will be refined. The most reasonable stance is patient rigor, test hypotheses, publish data, replicate analyses, and remain humble about claims that go beyond what the evidence supports. The universe has a consistent habit of surprising observers with phenomena that demand new categories. 3 Atlas has provided such a phenomenon. Its crimson glow, its odd chemistry, its apparent control of motion, and its other anomalies are not proof of anything beyond the data themselves. They are, however, a powerful reminder that the cosmos is larger, stranger, and more varied than our current models can fully explain. In time, the picture will become clearer. Further JWST observations, coupled with ground-based follow-up, will refine the spectral maps and the temporal evolution of the coma. Radar, polarimetry, and ultraviolet spectroscopy will add complementary views. Teams will test engineered shell hypotheses against better physical models. Biochemical patterning claims will be challenged with controlled simulations and laboratory experiments. And the global scientific community will continue to do what it does best: argue sharply, test rigorously, and publish openly. For those watching from outside the halls of science, the James Webb data about 3I/A/TLAS reads like a cliffhanger. It offers a long list of mysteries and a longer list of ways to examine them. The right response is to watch closely, to refine tools, and to let the data guide conclusions. The bad in the title might be the fear that comes from the unknown, but within that fear sits possibility. The possibility to learn more about the galaxy, about the variety of worlds that form in it, and about the processes that maintain complexity across vast temporal and spatial scales. Whatever the final answer for 3 Atlas, the episode will be remembered as a turning point. It is a moment when humanity looked up, trained its most advanced tools on a single object, and found that the universe had more to show than a simple tale of ice and dust. That discovery is not strictly bad or good. It is a challenge. It is a call to learn, to test, to prepare better, and to think more broadly about what might drift through our solar neighborhood. The James Webb data did not hand down a verdict. It raised questions. Those questions will keep astronomers awake at night, and that is how science advances, by trading comfort for inquiry, by turning alarm into method, and by allowing the cosmos to be persistent teacher.